Our lesson today is on frictional forces. So what's the goal? First of all, I can explain what a frictional force is, and then I can draw and calculate its value using concepts learned in class. So basically, we're going to now be able to understand, calculate, and explain frictional forces. So filling in our definition here, a frictional force opposes motion. Keep the definition simple. If an object is moving left, friction is right. If an object is moving up, friction is down. So drawing the vector representing friction, it will point in the opposite direction of motion. So in the grade 11 course, it's fairly straightforward. Grade 12, when we get into a pulley system or a weight system, we kind of guess at the direction of motion. And if we guess wrong, then we got to kind of redraw our vector in the opposite direction. So if we have F unbalanced this way, your force due to friction is in the opposite direction. So it always points in the opposite direction of the unbalanced force. Okay? So there we are. So let's look at some examples. So from the lab earlier, this unit, we can determine the formula due to friction. So everyone hopefully has completed the lab by this point in time. And what we found is this linear relationship. And just as a quick refresher, we put frictional force on the y-axis, and it was measured in newtons. This is when you're dragging the shoe. This is the sticky shoe lab. And then you put how much the normal force was, or the weight of the shoe. And what you did was you plotted the 3 or 4 points, used your line of best fit to get it turned out to be a linear relationship if you did it properly. Once you take that linear relationship, it means we can find a slope. So the slope must be fairly important. So if we take our rise and our run to develop, take a look at what happens. So we know slope is rise over run. So if I replace that, slope equals rise will be force due to friction, it would be delta, over the change in the normal force. We end up with a linear relationship or a constant. So once that relationship was discovered, what physicists then did was said, okay, we're going to replace m, because m just represents general slope. Here I want to talk about specific slope, and they use mu. Greek small m, not mu, mu. And that is equal to force due to friction over the normal force. And the formula you want to put on your cheat sheet or summary sheet is force due to friction equals mu multiplied by its normal force. So there's the actual formula. That's going to be kind of handy. If I jump over to the side for a second with this formula and do a unit analysis, so we end up with mu equals force due to friction, which is measured in newtons, divided by force normal, also measured in newtons. We end up with the units newton per newton. So for every newton of force, another newton results, and if you do newtons divided by newtons, it turns out to be a value of 1. So therefore, mu has no units. It's unitless. Okay? What it is, it's a conversion factor, if you want to think of it. It tells you how much frictional force is being converted, how much normal force is being converted to frictional force. So what percentage of the normal force is being converted to a frictional force. So it's kind of like, and it is, in a certain extent, a percentage of that normal force. So mu depends on the surface. So I'm going to add that stuff down below here. So mu is a conversion factor. I'm going to put that in quotations. Is a conversion factor of what proportion of normal force is being transferred. I'm losing control here. Transferred to frictional force. Okay, so it's kind of a conversion factor, and it depends on the surfaces that are interacting. All right. So your mu is a conversion factor. How's it measured? Well, it really depends on what the surfaces look like when they're interacting with each other. So, going back just to finish that thought off. Okay. If the two surfaces interacting look like this, so we're going to zoom in with a microscope, and it looks like this. There's the two surfaces. They look fairly flat. Then mu is low. Okay, that mu value will be low because two smooth surfaces are not too hard to rub together. If the surfaces look like this, a little bit more jagged, so we're looking at the microscopic level, remember? Okay, so that surface is a little bit rougher, then it'll be high. Okay, because it takes more work for us to pull two surfaces that look like that. So there's a higher conversion of frictional force. So this comes back to that whole formula. Why is normal force so important? Okay? So if you remember from before, so this is a recall, normal force is equal to force due to gravity plus or minus the applied force in the y direction. So that's already on your formula sheet. I spent a significant amount of time on that. Very, very important. Well, if that interaction force, if the interaction between two surfaces is dictated by the amount of normal force, okay, how tough is it to pull the two surfaces together? So if we're rubbing the two surfaces together, then if you increase your normal force, then you're going to increase your force due to friction. So in this case, for this picture here, force due to friction would be the interaction multiplied by the normal force, which would be mu Fg. So think of it as this is a box, and it's being rubbed over that surface. What happens if you were pushing down on that box? So same thing, here's the box, here's the same surface, nothing's changing there. We are going this way and this way. All of a sudden, on top of gravity, you start pushing at this angle. What that does is it adds to your normal force. You are now pushing down harder. So now we have force due to gravity plus that force in the y direction. So that formula, force due to friction, is equal to mu F normal force. It's to be mu multiplied by force due to gravity plus that extra force being pushed down. So there's more force available to be transferred into frictional force. So if you push down on an object while you're pushing it across the floor, you are increasing the force due to friction. If you pull something, okay, if you were to pull something, so let's put, this is a push, and I'll put an or in here, so there's a break. Force due to friction would equal mu force due to gravity minus Fy, because now you're pulling upward, then you'd have a pull. So pulling an object reduces the amount of friction. Okay? So pulling an object can reduce frictional force. And if you don't remember the why, go back to the previous, when we talked about calculating normal force, why it's so important, and it explains why that is. Okay, so pulling an object can reduce the frictional force, and that's because of this right here. Now it's subtracting that value, whereas before we were adding. So very, very important. That's why that normal force is so important when you're calculating force due to friction. Very, very important with that. All right, so types of friction. So types of friction, there are two types of friction. There is kinetic friction. And then over here we'll go with static friction. So what's the difference between the two? Kinetic occurs when there is motion. There is motion. And we go with mu k to introduce kinetic. Static friction occurs when there is no motion. And we use mu s to indicate that. Okay? Now, always, and hopefully you've discovered this in the law, or in the lab, sorry, that kinetic friction is always smaller than static friction. Always. Okay? So kinetic friction is always less. That's because it's easier to keep an object in motion than it is to get it started. So mu k, kinetic friction, is always less than static friction. You've already got something sliding. It's easier to keep it sliding than to get it sliding. Okay? And also remember, please, that any mu value has to be between 0 and 1. You cannot have a negative mu value, and you cannot have a value over 1. All right, so there's your stipulation when it comes to your coefficient of static friction. All right, and I think maybe I better put that official in your notes back here. I did say it was mu. Sorry about this. If you slide back, this is the coefficient. Just to make sure it's official in your notes, coefficient of friction. That's what that mu is. Okay, so our coefficient of friction is what it's called. All right, I will finish up with an example in the last video, and then you can try some friction questions.